Good morning, good afternoon, everybody. My name is Raj. I'm with Moser Baer Technologies. I'm the group CTO for the company. Thank you, Chairman, Professor Vikram Kumar and Professor Blakers for having me here, and to Professor V.K. Jain for inviting me to talk about what we're doing at Moser Baer. What I thought I would give you a broad overview and glimpse of what we are doing down the expressway 40 minutes away from here at Moser Baer. I'm going to describe, give a kind of an overview, and we can talk in more detail with anybody who's interested on any particular topic. I thought this would be a better way to tell a diverse audience what is happening in India, in Delhi, right here on photovoltaics and associated technologies, and then maybe look for a room for collaboration with other laboratories. So I'm going to talk about sustainable energy technologies. PV, which is photovoltaics included, but also talk a little bit about organic LED, which is energy efficient lighting, just to give a glimpse of the kind of activities across the Moser Baer R&D labs. So in Moser Baer, we are already in mass production of solar cells and modules and installation of PV systems in India and other parts of the world. The subsidiary company of Moser Baer India Limited is Moser Baer Photovoltaic, and I was the head of that for about a year from 2007 when we set up these facilities. Some of my colleagues are in the audience and would be able to answer more detailed questions of what is going on in Moser Baer. So in crystalline silicon PV, we have an 80 megawatt cell manufacturing line in production for the last 2 years, and an 80 megawatt matching module production line. In terms of real numbers on a day-to-day production basis, 80 megawatt cells is equivalent to about 1 million wafers of silicon 6-inch wafers per month. And in the terms of modules, 80 megawatts is equivalent to 1,200 watt modules of 60 cells per day. So it's fairly extensive 24/7 operation of production, and that's a crystalline silicon part of it. And we are now that the dreaded 2008 is gone, we are planning to get back in and expand our capacities. Doubling capacities. We see a market, and there's a demand, significant demand in the crystalline silicon area. On the thin film side, we are and I'll tell you a little bit more about the crystalline silicon line and associated activities going on in terms of supporting R&D. In thin film PV, we are focused in production on amorphous silicon technology based on thin film cells going towards tandem devices, and we're using an applied materials Sunfab production line, and that's we are the launch customers for applied materials. We have had it for about a year, and the capacity is about 35 to 40 megawatts of capacity, and we think it's a suitable technology for the Indian market, where the solar insolation and the temperature plays into the strengths of amorphous silicon despite its lower efficiencies. We did do a lot of concentrated PV in terms of production technologies, working with a company called Sole Focus, and manufactured OEM bases for them. Those are gallium arsenide 500x concentrated solar cells. We're doing less of it now, but we are capable of doing it at any point in time, high concentration solar cells. In addition to all this, the fourth bullet over there is the PV systems, and we're doing several off-grid installations in India, as well as grid-connected solar farms also in India, and some other projects in southern Europe. So why are we doing all this? We think through economies of scale and our experience in optical media manufacturing. We make a lot of optical media discs in the same factory location in Greater Noida. Just to give you a magnitude of the scope of scale here, we make 4 billion discs per year, optical media. So we are used to doing high volume production and thereby lowering costs and efficiencies of supply chain and so on. So that's the PV in production, and supporting all this for the next generation improvements of these are the R&D efforts. These are our milestones in this next slide of where we came from. We are a very young company in the photovoltaic field. We broke ground in August 2006 and got into production late 2007, and we've been doing it since then. And the thin film technology, which has been the latest to add on to production line, uses a very large glass substrate as shown in that picture on the top. It's a 5.7 plus square meter size substrate. And everything, obviously this cannot be carried, everything is robotics in this factory. So what are we doing in terms of R&D? So we have 4 thrusts in R&D area. We can call it basically 3 labs and the R&D outreach office. In the silicon, Moser Baer Photovoltaic company, which is doing all the crystalline silicon and thin film, we are doing the crystalline silicon cells, modules, R&D. We have a full-fledged R&D lab independent of production with state-of-the-art tools and can do 50 wafer batches of 6-inch wafers. And our thrust there is on a monocrystalline 20% efficient structures and cells for next production line, and for multicrystalline cells an 18% target for making this happen in terms of developing the process technology, differentiating it and learning from experience and implementing on the next line that we'll put in. So that's the one, the quadrant on the top left hand side, and in the top right hand side is our strategic technologies R&D lab, where we are focusing on emerging PV technology. I'll tell you more about it. Mr. Ivan Saha, I don't know if he's here or not, heads the one on the left on the silicon PV, and Dr. Rajiv Jindal, who may also be here, is heading the one on the right, so you may want to talk to him if there are questions on those aspects. In addition to that, we have R&D lab in Netherlands, in Eindhoven, which is a group of people came out of Philips that are expertise in optical media technologies, but we see a lot of synergies between what we do in optical media, thin film technologies, things like what the previous speaker talked about, the plasmons and the gratings and things of the sort. We are trying to apply some of these concepts to thin film morphosilicon as well as organic solid state lighting. So in the case of thin film morphosilicon, it's a question of scattering light and incoupling of light into the thin film cells. In the case of organic solid state lighting, it will be the outcoupling of light that is trapped inside the thin film device. In addition, we're doing some university support sponsored research in Japan on more fundamental aspects of material science, of epitaxy by sputtering, etc. And the reason for emphasis on many of our technologies in sputtering is we have a lot of experience in sputtering from the optical media and have significant assets on the ground, which if we can reapply to some of these new areas, gives us enormous scale. So there are 4 thrusts across the world, and then right now we are starting another R&D activity in the United States on organic solid state lighting. So this is a kind of this slide shows a layout of a 80 megawatt cell line. It's a horizontal processing facility. The wafers flow in from one end to the other, starting in the bottom right hand side of this chart and proceeding through cleaning, diffusion, PSG removal, then anti-reflection coating, which is the PVD section on the turn on the right hand side, on your left hand side, and then proceeding to the printing, drying, and testing. So the cells are going around at about 3,000 wafers per hour, so fairly fast, and this gives you that the million wafer per month activity. In support of this, we have developed some wafer inspection technologies and also module inspection technologies for production. Wafer inspection technology is, when you use so many wafers, it's important to screen good quality wafers from bad quality wafers. They come from all parts of the ingot and they're not all the same. And we're trying to screen it out by automatic filtration of the good cells from the bad cells in a machine that is shown on the right hand side that was developed by our team along with equipment partner in Japan, which measures all the physical parameters as well as the lifetime and other surface blemishes, defects, and etc., and puts them into various bins from which we select to put in there. So it's 100% wafer inspection technology. This gives us now a tool for dealing with vendors of substrates. Okay, so to make sure that the distribution of performance is narrow, and that when we change the processes, we know what the cause is, what the effect is. This is an example of micro crack detection and lifetime measurement coming out of this kind of machine. And here's an example of a module, full module EL inspection system, also developed for supporting our module line. This shows a 200 watt module with 60 cells and with all the electroluminescence measured on the spot. In addition to the standard things, we're also doing a lot of things to improve the efficiencies on the current line as well as the next line. Strategies such as reduced finger width. We are currently implementing 80 micron finger width into full production. Decreasing silicon material in terms of thin silicon, thinner silicon, and other back surface field. I will not go into these kind of details, but some of these standard things that you have to do to squeeze more efficiencies out of the device and therefore reduce the dollars per watt is being done. These are some of our installations in this picture of PV systems that have been come out of a factory and found their way into Europe or in India on rooftop installation. This is in India, in Gujarat, in the western state of Gujarat, in a place called Surat. Thin film PV, we are dealing with large substrates, and the picture on the right is the concept of a SunFab tool, and we are dealing with generation 8.5 technologies. And what are the challenges here, which is transitioning from single junction PIM amorphosilicon device to tandem to increase the efficiency to the 10% barrier, and then to improve optical design for light collection, which includes the scattering concepts that similar to the plasmon concepts that Dr. Bhattacharya talked about, and improving attack time, uptime, substrate, productivity, that sort of thing to bring costs down. One of the biggest cost items is glass with the TCO. So there is some activity that we are doing in that direction. And we haven't done much microcrystalline activities on the production line, but we are supporting this with activities in Netherlands for coming into the production line next. So the picture on the right-hand side is where we want to go with a glass substrate, a transparent conductor with a light incoupling strategy, and then a amorphous silicon top cell and a microcrystalline bottom cell. And this device optimization is happening in our Eindhoven research labs, and the scaling aspects of the gratings is happening also there. There's some more examples of the kind of things we're getting about 6.5% stabilized efficiencies from this line. Yeah, this is the work of Sudhir Kumar here and Dr. Rajiv Arya, who's the CEO of the PV business. So what are we doing in light trapping? In light trapping, we know how to make these periodic structures on substrates. So we're using these periodic substrates to independently control texture by lithographic process and to create a defined diffraction of light into the amorphosilicon layer. So we made things like that. These are published at the PVSec in Hamburg and Valencia. So there are papers behind this that one can look at. So we varied the grating period and optimized the AZO coating on top of the gratings, thereby decoupling the surface texturing by depositing and etching, which is the traditional approach, to creating the texture and then depositing the TCO on top of it. So in this case, we have optimized to a 300 nanometer, 600 nanometer, 300 nanometer height, 600 nanometer period. Okay. So 300 to 600 nanometer period to get the best coupling of light. And the short news of this is that we have compared this with standard Asahi standard glass where light is coupled, and is fairly good from that performance point of view. So there's a 30% relative improvement to the status quo by doing these structures. The question now is on scaling and trying to make tandem cells on it and optimize our overall structure. So the impression I want to leave with you is 20-18-10. So 40% for crystalline silicon mono, 18% target for multicrystalline efficiencies, and a 10% target for thin film amorphosilicon solar cells, all towards the production technology. Other significant PV technologies, we are working on SIGs solar cells and modules by sputtering and salinization method. Organic solar cells and modules, we are collaborating with a large US company on OPV and bulk heterojunction devices. Dye-sensitized solar cells. These are all exploration for the rural off-grid market, see if we can make a difference in India. We are going to manufacture junction boxes in India in support of the PV industry, and that activity is also proceeding. And then this other thing I talked to you about is a sponsored activity on thin film epitaxy by sputtering in Japan. So one more slide on lighting, and I'll leave, okay? So we are working on energy efficient lighting, which also is kind of complementary to energy generation on not the LED aspect of it, but the one on the right hand side, the organic LED, where I have a lot of personal experience in this field, last 15 years working at Eastman Kodak Company, and we're trying to use some of that knowledge to bring lighting rather than displays to the market. The display market looks like it's a $6 billion market by 2018 with organic solid state lighting. And with this approach, we're partnering with a couple of lead customers in the US and a major phosphorescent technology provider in US called Universal Display Corporation. And based on this technology, recently Moser Technologies and UD's Universal Display Corporation, we received a US Department of Energy award, very competitive award for $4 million last month, and a Dutch award for another close to $1.5 million in support of these projects. So these are our basic R&D activities in support of sustainable energy activities, PV as well as energy efficient lighting. Thank you for your patience. I took a little bit of time. Yeah.